Electrolysis is a promising option for carbon-free hydrogen production from renewable and nuclear resources. Electrolysis is the process of using electricity to split water into hydrogen and oxygen. This reaction takes place in a unit called an electrolyzer. Electrolyzers can range in size from small, appliance-size equipment that is well suited for small-scale distributed hydrogen production to large-scale, central production facilities that could be tied directly to renewable or other non-greenhouse gas-emitting forms of electricity production. Schematic of a polymer electrolyte membrane electrolyzer. How does it work? Like fuel cells, electrolyzers consist of an anode and a cathode separated by an electrolyte. Different electrolyzers function in different ways, mainly due to the different type of electrolyte material involved and the ionic species it conducts. Polymer electrolyte membrane electrolyzers. In a polymer electrolyte membrane (PEM) electrolyzer, the electrolyte is a solid specialty plastic material. Water reacts at the anode to form oxygen and positively charged hydrogen ions, protons. The electrons flow through an external circuit and the hydrogen ions selectively move across the PEM to the cathode. At the cathode, hydrogen ions combine with electrons from the external circuit to form hydrogen gas. Anode reaction: 2H2O right pointing arrow O2 plus 4H plus 4E. Cathode reaction: 4H plus 4E right pointing arrow 2H2. Alkaline electrolyzers. Alkaline electrolyzers operate via transport of hydroxide ions, O, through the electrolyte from the cathode to the anode, with hydrogen being generated on the cathode side. Electrolyzers using a liquid alkaline solution of sodium or potassium hydroxide as the electrolyte have been commercially available for many years. Newer approaches using solid alkaline exchange membranes, AEM, as the electrolyte are showing promise on the lab scale. Solid oxide electrolyzers. Solid oxide electrolyzers, which use a solid ceramic material as the electrolyte that selectively conducts negatively charged oxygen ions, O2, at elevated temperatures, generate hydrogen in a slightly different way. Steam at the cathode combines with electrons from the external circuit to form hydrogen gas and negatively charged oxygen ions. The oxygen ions pass through the solid ceramic membrane and react at the anode to form oxygen gas and generate electrons for the external circuit. Solid oxide electrolyzers must operate at temperatures high enough for the solid oxide membranes to function properly, about 700 degrees to 800 degrees Celsius, compared to PEM electrolyzers, which operate at 70 degrees to 90 degrees Celsius, and commercial alkaline electrolyzers, which typically operate at less than 100 degrees Celsius. Advanced lab-scale solid oxide electrolyzers based on proton-conducting ceramic electrolytes are showing promise for lowering the operating temperature to 500 degrees to 600 degrees Celsius. The solid oxide electrolyzers can effectively use heat available at these elevated temperatures, from various sources, including nuclear energy, to decrease the amount of electrical energy needed to produce hydrogen from water.